Well, it is 9 p.m. now in Hong Kong, and may I say good morning, afternoon, and evening to everyone. Welcome. I'm your host today, Hyson. I'll be moderating today's session. I have a couple of quick housekeeping notes for you. First, today's session is being recorded. Second, please keep your microphone muted while the speaker is presenting. Please hold all questions until the Q&A time at the end, and feel free to type in the chat. I'll read those questions aloud. Then it is my pleasure to introduce our speaker today, Daniel Bochen. Daniel is a Harvard Quantum Initiative postdoctoral fellow. He's mainly working on circuit and layout synthesis for fault-tolerant quantum computing with a focus on neutral atom array platform. He holds PhD in computer science from UCLA. Please join me in welcoming Daniel.
Thanks for the introduction, Hassan. So, I actually, my talk, there will be two parts. For the first part, I'll mainly just tell you what this title means. So I'll just basically state the result. And then in the second part, we'll dive into some of the details. For example, like how exactly are these quantum regression codes defined? So maybe we can actually do some Q&A in the middle, and then not holding off all the question in the end. I'll let you know like when I'm ready to answer some questions. Great. So I'll begin. Um, so I think at this point it's pretty clear that we need error correction. And the reason is that although our quantum computing hardware has been advancing for many decades, uh, so far the physical error rate of a typical quantum operation is like 1 in 1,000 to 1 in 10,000. But to run meaningful quantum applications, people believe that you need 1 in minus 12 error rate. And to bridge that gap, probably the only scalable way is quantum error correction. There are some standard approaches developed over the years. The most famous one is using surface codes, and there has been like very promising demonstrations of these kind of codes. However, recently people have been also interested in this good qLDPC codes. And the term good here mainly means that they have higher encoding rate. And as a result, we expect to reduce the number of physical qubit required by 1 to 2 orders of magnitude compared to the surface code implementation. With quantum error correction, we have a different model of operation compared to classical communication settings, where probably you've heard about this term error correction for the first time. And in the classical communication, we encode our message with redundancy, and then we go through some channel, and then we decode in the end. With quantum computation, we are not just maintaining the information, we're actively manipulating this information while they're encoded. So we'll have logic when the message is encoded with redundancy. And one fundamental um, thing to do in the middle is what we call synonym extraction circuits. So these are needed to gather information about the errors that happen, and you must frequently insert them between your logic. So these circuits are fundamental and frequently used in fault-tolerant quantum computing. Um, so it is important to construct them with a nice property, and one of the property people focus on is circuit depth. There are some bounds on the circuit depths on the lower end, you cannot go beyond this tanagraph degree delta, which we'll see more uh, later. And there is also this coloration circuit construction that is at most 2 delta. So the previous works just falls between these two bounds. For many specific codes, we have construction that reach this tanagraph degree. For example, for surface code, the circuit is very well known. And our main comparison for previous work is this PRA paper published a few years ago. It works for a strict subset of the codes that we work on. So these are hypergraph product, which we'll see in the later slide. And their construction, I would say, it's not particularly complete because like it may require this code to have some property, and that property may not be um, very easily computable for all the codes. And in general, their construction falls between probably looks like a Gaussian, like the depth they can reach probably falls like a Gaussian curve between the two upper and lower bounds. And for this work, in comparison, we construct circuits with depth delta or delta plus one, and it's a more general class of codes than HGP. This problem essentially comes down to um, assigning time steps on this tenor graph. So what is this tenor graph? For any CSS code, which just means you have some X check on the data qubits and some Z checks on data qubits, nothing mixed. We can always represent it with this tenor graph, where we have 3 sets of checks. We have 3 sets of vertices. We have X checks here colored in red, and Z checks here colored in blue. So each check vertex connects to a few data qubit vertices. Those are the support of the check. The constraints for this problem is that first, you cannot have conflict at each vertex, which just means if you look from each vertex, maybe you look from this X check, then all the time steps you assign to the edges that incident to this vertex must be different because we are imagining each edge here will be 2-qubit entangling gates in the circuit, and you cannot have more than one entangling gates on 1 qubit at a single point in time. The second constraint is probably the more non-trivial one out of the two, is what we call timing consistency for each XZ pair. And that just means X is earlier than Z for an even number of times. This is the general statement. If you think about the CSS code construction guarantees that each X and each Z check share an even number of common neighbors, which are all data qubits. So that's a property called the commutation between X and Z checks. And for example, these two checks, they share 2 data qubits as their common neighborhood. And if we have this scheduling, then it is fine because on both of the data qubits, X check is earlier than Z check. So 1 is less than 2 and 3 is less than 4. In comparison, the figure shown on the bottom right corner, we don't have a conflict at any edge. But this timing consistent constraint is violated because X is earlier on the left data qubits, but X is later on the right data qubits. Okay, so now we want to understand a little bit more about the specific code family we are working with. And it is the structural property of this kind of codes that enables us to construct the near optimal depth circuit. We first introduced this subclass, hypergraph product, which the previous work talked about. So these kind of codes, you start with two classical codes. A classical code, like we have seen the quantum tenor graph, and this is just the classical tenor graph, which is simpler. You just have two types of checks. You have two type of vertices. You have bits, which are the circles, and you have checks, which are the squares. And the edges just connect the check to its support. In this example, you just have A and B are the same, and then it's just I think it's called a single parity check code. So you always have one single check, and then it's like support is all the bits. So you just check the parity of all the bits. With hypergraph product, you take so this is actually very interesting. Anecdote is that a lot of times people say tensor product of these two graphs, but actually that's not true. I think if you look on Wikipedia, it's called Cartesian product, um, which is from A and B, you have four types of qubits. So if you have a bit on A side and a bit on B side, then you have a left data qubit, which are drawn here. And then if you have check on one side and bit on the other side, that will produce a check qubit. And depends on like whether it's like bit A check B or bit B check A, you have different X and Z checks. And finally, when you have check A and check B, you produce right data qubits. Here, there's only one. The connection of the quantum tenor graph simply you just like interpolate the classical tenor graph. So these are all the edges in the quantum tenor graph. The key of this construction is that when you do this Cartesian product of two classical tenor graphs, you guarantee that commutation relation between the X and Z checks. And the hypergraph product is actually one of the first known families that can produce good qLDPC codes back in 2014. So that is a pretty fundamental. The more general family we're working with is called lifted product. And here you can elevate each of the vertices on the left to a super vertex, or actually we call them lifted sets. And then also you can have a multigraph, which means even between the same pair of bit and check, you can have multiple edges. So the quantum tenor graph is again the Cartesian product of these two multigraphs. And in each of these super vertex, actually you expand it to multiple elementary vertices. Here we have three, and this is called the lift, or if you look at the graph, it's called a lifted graph. And the reason that you can have the different multiple edges between the same pair of super vertex is because you now actually have edge labels, and these labels are specific how you couple the elementary vertices inside. So you can couple them differently. That's why you can have multiple edges. And similarly, for the quantum tenor graph, you also expand it to elementary qubits. Our construction for the syndrome extraction circuit, we start with optimal edge coloring of the lifted multigraphs. This can be done efficiently because these graphs are still bipartite graphs. And we perform this schedule in time. There are three stages: early, middle, late. For the middle stages, we apply all the C naughts that um, come from the classical code A, which are in the vertical direction. So this will require delta A layers. And for the early and the late stage, we kind of do this twist. So notice that we split the colors into two as even as possible sets. So here we have three colors, and then we are forced to have like two colors on this B less than and one color on B greater than. If we have an even number of colors, we'll have the same number of colors. And this twisting, it happens because you have for the edges induced by B, they are so some of those are start from the X check, some of them start from the Z check, and we have B less than or B greater than differently on the X and Z. So in this example, in the early stage, we apply B less than for the Z, which are the blue diamonds, and B greater than on the X, which are the red squares. The late stage exactly reverse the early stage. The meat of this paper is actually proving that this is a correct syndrome extraction circuit, which I will go into in the second part. But I think it's sufficient to understand what the result is without going through the proof. And it's easy to see that our circuit depth is delta or delta plus one because delta is delta B plus delta A. And the middle stages, we have delta A, and the early and late stage, we have delta B divided by 2, taking like the saving. And that is exactly because if B has a odd number of colors, then that's what happens. Let's look at a few generalizations from this core construction. First, there's plenty of freedom. For example, our choice of what colors are B less than and what colors are B greater than is totally at ease. Like whichever separation works fine. And there's like many more, which I'll also go into the second part of the talk. We generalize this to higher homological dimension, and yeah, it's kind of hard to explain what exactly that is, which I also do in the second part. But I want to mention that this kind of codes enable the state-of-the-art space-time volume for magic generation, which is believed to be the hard part of quantum computing compared to the other Clifford part. We also generalize this to a pipeline version. So the difference is that now some of the gates in the current round overlays with some of the gates in the next round, which is the X prime here. This also covers the specific construction in this paper. Okay, so as I said, like the first part of the talk really just enables you to understand what the title says. What we're doing, we're constructing syndrome extraction circuits. We can do that with near optimal depths, which means tenor-graph degree delta over delta plus 1. And also specifically, this result is arrived on specific quantum architecting code families. And here it is a quasi-abelian lifted product. And that actually covers most of the high-rate qLDPC codes people consider practical. As future direction, it is first fundamental to understand what is the limit of this construction. We'll see in the second part that you can't actually remove this quasi-abelian to general lifted product codes. There will be some issue. But I think it's fair to say that we are still investigating what is the fundamental construction, what is the fundamental limitation. And the second direction also is important. So we optimize depth, which is important in many ways, but also we probably want to use that as a solution space, and we want to select the best fault tolerance performance out of this optimal depth circuits. We've already open sourced the code, and you'll also find the manuscript in this GitHub repo. And I'd like to acknowledge my wonderful collaborators. To rewind a little, we have introduced hypergraph product code, which which is basically this product of these two classical Tanner graphs. And our problem is that for each of the X check, you need to apply these CNOT gates controlled on the check and target on the qubits. For example, here, like from check 1 in the middle, we have 3 purple edges coming from A connecting to left data qubits 147, and then 1 horizontal edge connecting to 9, which comes from the classical code B. And for each Z check, you also you initialize a measure in a different basis compared to X check. And then for the C naught, you control on the data qubits and target on the check qubits. In this specific example, we can compare, we can pick one X check and one Z check. I think it's X check 1 and Z check 2. You look at their shared neighborhood. And in this example, it's qubit 9 and 7. And this is the consistency constraints we mentioned earlier. On the left, we have X check 1 is earlier than Z check 2 on both of the data qubits 9 and 7, which is their shared data qubit. So that just means for if you look at data qubit 9, X check first talk to it through a CNOT gate, and then Z check talks to it. On the for the scheduling on the right, it's not correct because we kind of flip the order of X check 1, Z check 2 talk to data qubit 7. In general, this is the expression you want to check. So for a X check Xi, Z check Zj, N here means their neighborhood, and because it's a bipartite graph, the neighborhood can only be data qubits. You take their common neighborhood, and for any cubic Q in the common neighborhood, you multiply this the time step of the X from X to Q and from Q to Z. So for each of the common neighborhood, you have this factor, we multiply them together, they should be greater than 0. That equivalently is saying when you have an even number of times in the common neighborhood that X is earlier than Z. And because by the construction, they have an even number of vertices in total, it also means there's an even number of vertices that X is later than Z. And then if X is earlier than Z, then this factor is positive. If X is later than Z, then this factor is negative. And since you have even number of both kinds, then this the total product must be greater than 0. Okay, so the total, the max vertex degree of the quantum Tanner graph is always delta A plus delta B. So this point I can gloss over in the first part. And it's very easy to see because you can always find um, a vertex in A graph and a vertex in B graph that reach the delta A and delta B, and then you just check the qubits that they produce. In this example, the max degree in graph A is a check, and max degree in graph B is a check. So you just check, then the max degree in the quantum tenor graph would just be their product, which is check times check is a data qubit 9. And since this qubit will inherit the edges in both vertical and horizontal directions, its degree will be delta A plus delta B. So this is a lower bound for a single round silicon-Silla syndrome extraction circuit depths. I also so this if you notice, this is like in the footnote of one of the slides when I state the result. So because there's actually multiple ways to construct syndrome extraction circuit. First, the single ancilla part. What I mean is you have a single ancilla qubit for each X check and a single ancilla qubit for each Z check. In general, you may have multiple, like if you have a bell pair, and then you can actually use that bell pair to connect, and then you have CNOTs to compare to connect to the support of the checks. But then you'll be using more than one ancilla qubit. So that's you need more qubits. So here we focus on single ancilla syndrome circuit, and also this optimal depth is for a single round. So this is actually a stronger compared to if you don't say single round, and that's because if you have multiple rounds, then maybe it is like our pipelined construction is that you can somehow amortize the cost when you consider the average over many rounds. But if you have a single round optimal depth, then you can also just like repeat it to have multiple rounds optimal depths. So single round is stronger. Our result is like I've introduced, we have delta or delta plus one for QLP codes. And that is also very interesting because we know that delta is a fundamental lower bound. So we are at most plus one from optimal. So this is similar to generic graph edge coloring. So if you are familiar with graph theory, you can do edge coloring of any graph um, with delta or delta plus one colors. So this is edge coloring. It's not vertex coloring. Edge coloring just means you color the edges so that um, if you look from each vertex, all the edges have the different colors. Okay, so for if delta B or delta A is even, we our construction give depth delta. If both of them are odd, then our construction give them delta plus one. And we also know that like since the fundamental lower bound is delta, right? We only have that means our result tells you that there's only two type of quasi-abelian lifted product codes. I call type 0 and type 1, which are those have optimal depth delta and optimal depth delta plus 1. If our construction gives delta, it's pretty clear. First, it's impossible that this code actually needs delta plus one because we already give a delta solution. And then if so it must be optimal. However, if our construction give delta plus one, the picture is less clear. So this is also similar to the case of edge coloring. It's actually NP hard to decide uh, which graph is type 0 and which graph is type 1 for edge coloring. In our case, for example, this very example I shown on the slide, we also have some SMT formulation to optimize the depth of a syndrome extraction circuit. And this one, delta A and delta B are both 3, right? Because the check has a degree 3. So our construction will give you plus 1. but that SMT found a solution with only 6 time steps. So that falls into this top right corner. And there's also some other examples we found and also proven with the SMT formulation um, that our construction give you $+1, but also the optimal is also $+1. So this is the HGP of 2, 4, 3 regular. No, not four. It's a complete graph of 4 bit and 3 checks. So, oh no, that's yeah, it is. Yeah, complete graph of complete biparallel graph, 4 bit, 3 checks, and then you take the hypergraph product. Okay. And also we want to introduce a little bit more about this QLP code family. We have seen this picture before, and I think the correct term actually is called for this kind of um, higher level graphs are called protographs. And the vertices inside we call it proto-vertex, which I referred as super vertex before. And also formally they're called L-lifted sets. And L is just the size it expands to. In this example, we have L equals 3. So this colored region is looking at the 2 edges between 2 proto-vertices, and each one will expand to 3 regular vertex. And each of these edges corresponds to a permutation of the L elements. And as I said, it can be a multi-graph. In this callout, exactly, we have two edges connecting the same pair of vertices. And they correspond to different permutations. And quasi-abelian just means these permutations are from a abelian group. In general, permutations are not abelian. So if you pick some abelian subgroup that give you a quasi-abelian property. In this specific one, we can label the vertices 1, 2, 3, and then the orange proto edge is this. So we are specifically considering cyclic group, which is just a map which apply a cyclic shift. The orange one is you connect 1 to 1, 2 to 2, 3 to 3 is its identity, and that is denoted as x to the 0th power. The blue one, you connect 1 to 2, 2 to 3, 3 to 1. That's a cyclic by 1 unit, and that's denoted x power of 1. So in general, you can have x0, x1, all the way to x to the L minus 1 power. And that here is x square. One question I ask a lot is that, okay, you introduce hypergraph product, you also introduce this lifting, but I can also first expand these protographs to, I can expand it to like a regular, just like a, basic biparallel graph, and then I can take the hypergraph product. So that is actually different from lifted product. And that difference is exactly why lifted product is more efficient. Because if you think of the lift sets, so if you first expand it, then each of these factor graphs will expand by L times. And then when you take the product, you'll have L square. That many, you expand the number of vertices to L square times. However, if you first take the product of the protographs, and then in the quantum ternograph, you expand this lifted sets, you only grow that by L. And that is the resource saving of this lifting. There's many examples that belongs to this family. If you don't have this lift structure, right? With hypergraph product, it's just a lifted product code, but the lift is one, L is one. And in the middle, you can have some hypergraph product structure, and also you can have non-trivial lifts. And the x monomial here are the lifts. And this comes from the, I guess, recently very famous paper by our Atomics saying, uh, well, their title is you can run Schur's algorithm with 10,000 atoms. On the other extreme, you can have no hypergraph product structure. So you only have uh, one um, one X, one Z, one L, one R, but each one is a lift. So you can have a very rich lift structure. And for this IBM code specifically, each lifted set contains 72 elements. And the lift, the permutation comes from this product of two cyclic groups, C12 times C6. And that give you 72. And then you have one L lifted set and one R. So these are your data qubits. So you just have twice of 72, which is 144. Okay, so also like to introduce a proof, we also need to revisit the scheduling strategy. Actually, here is probably still pretty fresh at this moment. Um, okay, so meat of the paper is actually the proof, and that's essentially pairing. So you pick an X and Z, and then you have some neighborhood, and then essentially this proof is about pairing them up. Because remember, because of commutation, there are always an even number of shared data qubits. So how do we pair them up? So suppose you pick this X and this Z, and so they belong. So the vertices here, these are still the proto vertex. So each one of these is um, represents L qubits. Suppose you have some path that travels from X to L data qubits by A, and then by B you travel to a Z proto vertex. Suppose you have this path EA and EB. Then by the hypergraph product structure, you always have the other side. You also always have like EB and EA. So and in this example, like so we find this L, right? So it's like traveling along this edge and then traveling along that edge. Because the hypergraph product structure and also the quasi-abelian, you always have the other side. Because because X will also have that horizontal edge of between L and Z. Because in I didn't specifically draw it here for visual clarity, but every column, every row will have the same edges of B, and every column have the same edges of A. So you can always find that kind of rectangle, the rectangle. You can always find R that kind of finish this rectangle. And then so I actually misspoke. Like here we don't actually make use of the quasi-abelian property. It's just a hypergraph product property. Where we use quasi-abelian is that, so we first identified this lifted set is that we look inside the lifted set. So suppose on the bottom left corner here we have we draw E and EB, how they shift the qubits around in the actually I shouldn't say shift, it's more like you couple the qubits differently, how they couple the different qubits between XL and Z. And suppose the specific check we consider is the highlight is the darker one. So from little x to little l to little z. The quasi-abelian property just tells us that um, you can actually find a little r where x to r is the same edge compared to L and Z, and then R to Z is same edge compared to X and L. So this is where the quasi-abelian property is required. Otherwise, if EA and EB, how they couple things, are not commuting, then you're not guaranteed that there is a unique R. Yeah. Um, so essentially on this page, we found that for each check pair X and Z, the shared data qubits can be paired. So we can split their common neighborhood into L1, R1, and L2, R2. And then actually it's pretty easy. So um, our construction will guarantee that for each of this pair, X is earlier to both of the data qubits, and or Z is earlier to both of the data qubits. You can never have X is earlier on one and Z is earlier on the other. So the example here is that why that works is that we put all the vertical edges, which comes from the graph A, in the middle stage. And then for the early and late stage, we have that twist. So for any of this kind of rectangle structure, you must the horizontal edges must come from one specific proto edge of B, and then the vertical edges also come from one specific proto edge of A. Because of that, and because of the twisting just means for all the edges induced by the same proto edge in B, if that edge connects a z-check, you are in maybe it's in early stage, that automatically means that same edge but connecting x-check in the late stage because of this twisting. And if it's connecting to z-check in the late stage, then the x-check connection will be in the early stage. You can never have both in early or both in late because of this twisting. And so like in this picture shown, right? Then x is earlier. X is actually later than z on both L and R qubits. And since we already paired the shared data qubits up, then in each pair you can take this product, and then that product will be positive, and then you multiply all the products for each of the pairs, then they're always positive. We have been pretty ad hoc in describing this construction. That's because it's easier to first have a valid solution, then look at what freedom you have. For example, we use the vertical edges in the middle, and the horizontal edges in early and late, but that's like arbitrary. You can also have the horizontal one in the middle and the vertical one in early and late. Any edge coloring for the protograph suffice. It doesn't need to be this specific edge coloring. And the early late stage assignment, which color goes into greater than, which color goes into later than, is also arbitrary. As long as you put them evenly. You like if it's even number, you have the same number of colors in early late assignment. If it's odd, then it's off by one. And also in each stage, you still have multiple layers, and the order of those multiple layers doesn't matter as long as you maintain this stage structure. Also, if you really want to explore, then you can actually assemble different colors in the same layer on subsets. For example, if you look at the early stage, like you have um, orange edge in the first layer and the blue edge on the second layer. So maybe just for fun, you can swap out the green edges to the on the first row in the first layer, and then you delay the orange edge on the second one, right? That also works. Um, so I see there's a question: if multiple valid pairings exist, does the choice of pairing affects the result circuit construction or depth? Actually, the pairing will be unique when you because yeah, you first identify the um, corresponding proto vertex by the hypergraph data structure. So that's unique. And also by the quasi-abelian of these permutations, you also find a specific unique elementary qubit. Okay, and this design freedom actually is leads to different fault tolerance performance, and that's why I say like in the future direction, we probably want to have some efficient way to figure out which ones are better ones. For this specific tricycle code that we can generate magic. We see that at 10 to the minus 3, which is typical assumed error rate, we can have like a order of magnitude out of this design freedom. So all of the lines here have the same depth, and that depth is optimal. But then some are doing better than the other in logical error rate. For generalizations, I mentioned two in part one, so let's just look at them more carefully. With 2D bicycle codes, we have so these are just lifted product codes with a trivial hypergraph product structure. And so we only have one X, one Z, one L, one R. And then you have like two of these terms between them. And for this, our strategy in this paper is called three-stage scheduling always works. The tricycle codes is just now you have a third dimension. So it's like multiplying this 2D uh, 2D protograph with a third one. And now you have actually three sectors of qubits, x1, x2, x3, three sector q1, q2, q3, three sectors of x checks, and then one sector of z check. And this dashed line I have here is actually what's called meta x check. So these are not real checks you need to perform, but it's just a property of this kind of codes that you have some redundancy in the checks themselves. So you're checking an over complete set of checks, meaning that there are some constraints between x1, x2, x3 values that they need to satisfy. And this can enable what we call single shot error correction because you have redundancy in your check. And then you can use those redundancy to compare the checks themselves so that, like you can catch some errors without going through the D cycles that we usually assume for error correcting codes. And since you have three dimensions, you have three terms, A, B, and C. And that's exactly what happens in this picture. Like on a higher level, it's just like we first handle the A and B. So that's in the middle. And then it's like just we sandwich it with C. And this actually goes beyond three-dimensional. Like for any dimension, you can you can just do this kind of constructions iteration. Then like with each dimension you add another layer. You add two breadths in the sandwich. But this optimality gap can grow with dimensions when you have like odd weight in this A or B or C terms. For example, with a 3D, you have 5 stages, and then the B and C, when you do this twisting, they can increase the depth by 1 each. So now our depth is less or equal to delta plus 2 instead of delta plus 1 for the 2D case. Pipeline schedule, probably not too much to say about that here. So here, when we say depths, we are only counting the depths of the entangling gates. And when you do this pipeline, you can you're not do that twisting. You're actually doing the B of LZ and the B of X and R for the next round together. So you're not doing that twisting. And because of that, you actually have always the delta number of layers on average when you consider many, many rounds. If it's like just a single round, right, then actually it's going to be depth is going to be higher because you are not overlapping the B part. So you have 2 delta B plus delta A. And I'd like to mention that there's a concurrent work released with our paper, this left-right circuit that is also leveraging this construction. And also for hypergraph protocols, this is called a staggered circuit. It's already covered in some previous work. Finally, I'd like to mention a recent generalization to this cycles. So these are interesting, like it's because they offer some crazy encoding rate. These are large codes, right? So these are like this specific one that I think like kind of break the news. You have over 9,000 data qubits, but you have 50% encoding rate. You have 4,000 or so logical qubits, and the distance is also good enough. These codes are constructed by this parent matrix. Here, prime means transpose. This looks in the kind of scary, but we notice that there is actually similar structure to the bicycle code. You also have this A, B, B transpose, A transpose structure. What it deviates from the bicycle codes is that the permutation, which are the F and G here, they do not all commute. With the bivariate bicycle codes, the bivariate part means it's a product of cyclic groups, and then those permutations always commute. Here, they don't commute, and actually, the rows here, which are the X check and Z, which should represent X and Z checks, actually some of these rows do not commute. So that is not even a valid quantum code. The trick is that we drop the bottom half of this parent matrix. And if we only consider the top 3 rows, they actually commute. That's like essentially how the breakthrough of this code family. And our strategy trivially applies here because it applies to this parent matrix. And then we drop the bottom 3 rows and it's fine. Like the construction still works. Where our construction doesn't quite work is some of these general lifted protocols. So these are not quasi-abelian lifted protocols. I found an example with help of AI. Is that this is a 14-to-3 bicycle code. So it's still a bicycle code, but this permutations comes from the general permutation group, which is not abelian. And this is the specific permutation. So for A term, you have 4 permutations. B, you have 4 permutations. So basically, that means in the protograph, you have 4 edges. A represent 4 edges and B represent 4 edges. And the reason that our construction doesn't quite work here is that you can't quite pair up the paths, or you can't quite pair up the data qubits. And specifically for X1 check and Z0 check, you have 1 path on the left and you have 3 paths on the right. and you cannot really pair them up. Then that's why we fail. And the non-abelian property here is pretty visible, right? So you have A2B0, right? This is traveling from X1 to Z0. If it were a quasi-abelian Lifted particles, you will also have B0, A2. However, there's no such path. So that demonstrates it's non-abelian. All right, so that actually covers everything I want to say. I will just display the GitHub link again for if people want to